So chapter 3.1 is kind of the second time that our book introduces the term of a vector. So we're talking about vectors in 2, 3, and n space. So two-dimensional space, three-dimensional space, and in general, that's what we need later is the n-dimensional space when we have more components. Even the term dimension will be only introduced in chapter 4, but in the moment, instead of dimension, just think about how many components your vector has. Okay, so until now, vectors are special cases of matrices, no? So they're either n times 1, that's what we call a column vector, or 1 times n, then we would call it a row vector. So their matrices are just special cases of, vectors are just special cases of matrices. And it turns out at the end, we can actually go back to this view again. But out of this section comes a little bit also an additional interpretation what a vector is. And that's also what you might have seen in physics classes about vectors. And so that's what we start now. We consider the plane. For us in the plane, in the moment is always my piece of paper here. That's our plane. And so we have in the plane, we have 2 points, A and B. So let's say here's a point A, and here's a point B. And then you can look at the straight connection between these 2 points. And besides this section of the line which connects A and B, we also give it a direction. So it's important if you go from A to B or from B to A. And we indicate this, for example, with this kind of arrow, which means we go along this line from A to B. So AB is the straight movement from point A to point B. So, and this straight movement, that's what we also can consider a vector, no? So AB is what we consider as a vector. So a vector is given by its length and its direction. So it can be, I hope I can do this kind of correctly somewhere, that there's another point C, and I try to make it kind of hopefully good, and another point D. Then you can have this connecting vector. And I hope my picture is good enough. But if you move the vector over here parallel, it turns out the vector is the same. So it's not just AB gives you a vector, that's true. But what we mean by the vector is every other connecting movement with the same length and the same direction. So my picture is maybe not the greatest, but the point is the same vector can also connect other points. And we would say it's the same vector. Even the connecting points are different. So it can be that AB is equal to CD. Yeah. So the vector doesn't have to start here. You can move it parallel around. Where now we have to introduce what does actually parallel mean, but I stopped there. I hope everyone has some kind of intuitive understanding of what parallel means. Okay, so once you have the idea that a vector has a length and a direction, suddenly you can do other things with vectors, no? So, for example, given a vector, let's say call it V, small v for vector, we can also find the opposite vector, minus v, in this following sense. So you have here a vector v, and then you just flip around 180 degrees. So if this is v, then this here would be minus v. So if this one, let's say, goes from A to B, then minus v would go from B to A. So, and you can do this without any math, also any arithmetic. You just flip vectors over. You can, it's purely geometry in the moment. Also, what you can do with vectors, if we have two vectors, v and w, for example, and I just make some examples here. So let's say this is v, and let's say this is w. You can move this vector to the end of the v vector. So you can do this, and then this. And it turns out the resulting movement is also a vector, which we usually would call v plus w. Turns out, when you think about it, it really doesn't matter which one you do first. You can also do w first and then v. And you would end up at the same vector. So it turns out, just from the geometry, v plus w is w plus v. Then finally, the last thing you can do is, if you have a vector v and a number alpha, so for example, v is this vector, and for example, alpha is 1/2, then alpha v, so if this is v, then maybe I should write instead of alpha, so alpha is 1/2, so we have 1/2 v would be just the vector up to here. So it's going in the same direction as v, but only the length 1/2. And for sure, you can also make it, for example, and make it easy, twice the length. So that would be 2v. And then you can take 1/2 v and flip it around. That would be minus 1/2 v. So the point is, once you have this geometrical concept, then you know what alpha v is. Vector times number. It means you stretch the vector, shrink the vector, or if alpha is negative, you reflect the vector. So purely geometrically, we can now say what we mean by adding vectors, multiplying vectors, and inverting vectors, and what vectors kind of are. So the advantage, if you have this picture of vectors instead of what we actually talked in chapter 1, in chapter 1 it was purely a game with numbers. You have blocks of numbers, you add them up, but there's no intuition. What are we actually doing here? This really tells you, oh, if you work with vectors, you actually do something which with objects, for example, in the plane or in space. You stretch them, shrink them, add them together. So, and that will help a lot with understanding a lot of the things with the intuition, what people do with vectors. There should be a geometry behind. That's, also now, essentially this section starts the idea, oh, what we did until now has actually a geometry to it. Okay, so the next thing is, and you have seen this also in school, the geometry is nice, but geometry goes in other directions. Geometry studies geometrical objects like triangles and find about angles between triangles. In linear algebra, it has always this kind of more number thing to it than what you see already when you look at matrices. So the thing is, once we have the idea, okay, these are objects in the plane, but now we like to calculate them. So we go a little bit, we go away now from the purely geometrical point of view. And the solution to this problem, how can we bring numbers into the geometry, is the Cartesian coordinate system. So now we are looking at the Cartesian coordinate system. So for example, in the plane, I cannot make pictures in 3 dimensions, but usually we would call this X and Y, and you have here coordinates. This is 1, 1, 1, 1. So suddenly a point is just not a point in the plane. A point has, for example, coordinates, like these points. No? So this point would be, for example, 1, 1, means 1 to the 1 direction, 1 to the Y. This point would be 3, 2. So now that we have points, so this, let's say, is point A, this is point B. Now that we have numbers to these points, not only can we say in geometry, oh, we mean now this vector, this line with the arrowhead. So now we can say, oh, the vector V is actually given by 2 numbers. We have to move from 1 to 3, 2 units to the right, and 1 unit up. So now we can say, once the points have coordinates, the vectors also get coordinates. And so in general, going on with this, so if the point is, let's say, A in the plane has coordinates x1, y1, and then B has coordinates x2, y2, the vector from A to B has coordinates x2 minus x1, y2 minus y1. And if you are in space with 3 coordinates, also this is now space, also 3D, you have x1, y1, and c1. So you have left, back and forth, and up and down. Then you have B, x2, y2, and c2. Then the connecting vector has coordinates x2 minus x1, y2 minus y1, c2 minus c1. So for example, I hope that's clear to everyone, that if you have a point A, which is 1, 2, minus 1, and a point B at 4, 0, 5, means, also if you have a coordinate system in 3 dimensions, I mean, I'm not sure if you can see this, something like this. So it means, for example, this point, you go 1 in this direction, 2 in this direction, and then 1 down, which I cannot do because of my table. And this point would be 4 in this direction, nothing back and forth, and 5 directions up, 5 units up. And so then the connecting vector, it's already harder to understand, but here the good thing about numbers come in, you can do it automatically, and you get in space the right connecting vector. 4 minus 1 would be 3, minus 2, and 6. So that would be the connecting vector. Okay, so this gives us an idea that these vectors now have actually meaning. Each component tells you how to walk. And now we have 2 components, 3 components. Yeah, we cannot imagine it, but why not more components? Also 4 components we can imagine. The 4th component might mean the time. Then you can walk in space and time. But in mathematics, there's no reason to stop at 4. So in mathematics, we see we can have n components. So in your book, I just combine all this together in definition 1, 2, and 3. So instead of having 2 or 3, we have now n components. So if n is a natural number, then an ordered n-tuple of real numbers, again, we only consider real numbers, we will not do complex numbers, at least not for vectors and matrices, is a sequence of n real numbers. And we can write it like this, we can write it like this, like what I did here, v1, v2, up to vn. But from the beginning, I also like to always go back and use my column vector notation. The book doesn't do it, but I just like to stay with this notation, even for the vectors in chapter 3. And so And this is a tuple, and it's called a vector. So a vector is an ordered tuple of n real numbers. The only difference to chapter 1 is if there are now 2 or 3 numbers, we say, oh, if there's a 5, it means there's a direction and I got 5 in this direction. If there's a 3, it means I go 3 in this direction. If there's a -2, I go -2 in the other direction. So suddenly, it's not like before they're just numbers, and for example, x is a solution of a linear equation system. Now we think about these numbers that they give us essentially orientation in space. And okay, if the space is 10-dimensional, it's a little hard to understand what this means, but they're just 10 dimensions and we can walk around in them. Okay, and so, and again, the set of all these numbers, same thing as what we did in chapter 1, we call our n. Vectors is called the real number symbol, and then an n here on top means it's n copies, 1, 2, 3 up to n copies of the real numbers. Okay, and so what can we do with these vectors? Same thing as in chapter 1. We can add, subtract, and multiply by numbers. So for 2 vectors.
Professor?
Yes?
I'm sorry, what does the first sentence say right above the all real numbers to the n?
Oh, the set of all these vectors is called Rn.
Perfect, thank you.
So you make a bucket with all the possible vectors, and this bucket is called Rn. Okay, and if you have 2 vectors in Rn, I always write this here, means in Rn. I write this already since last week, but I hope by now that it's clear what it means. Then we have, for example, V is V1 to Vn. W has also n components. Then V plus W, similar, also nothing has changed, is V1 plus W1, V2 plus W2, plus Vn plus Wn, so add by component. And if alpha is a real number, alpha and R, then alpha V, again, so nothing what you learned in chapter 1 is wrong. It's just, there's a new interpretation to it. It's just alpha V1, alpha V2, alpha Vn. So we do everything the same as in chapter 1. The only thing is, now when I say a vector and I multiply by 2, okay, like in chapter 1, the 2 goes to every component, but in my head is now also the picture, oh, the vector is a certain vector. Multiplying 2 means make it twice as long, keeping the direction. Yeah? So the only thing is really these two or three pictures which I gave you at the beginning, that suddenly we say, oh, these things are actually directions. Okay, and then the last thing is the inverse vector. Negative V is just the vector where every component gets a negative sign. And then V plus negative V is all 0 vector, and most of the time I just write a 0 for this. Sometimes to emphasize, is this now the 0 number or the 0 vector? Sometimes I make here now an arrow on top to indicate, oh, this is really a sequence of zeros, that's the 0 vector. Okay, so we have now this the collection of all vectors, which we call Rn. So this is what we call later a vector space. We know how to add them, multiply by numbers, there's an inverse, and there's a special vector 0. And now we write down the properties of this vector space. And they're exactly what we have seen in chapter 1. So that comes now the second time, and it turns out the same thing comes a third time in chapter 4, when we say whatever behaves like this, we call a vector space. And maybe it's not a tuple of numbers anymore. So whatever acts like this, we call a vector space. So again, it will show up in chapter 4 again, but I write it down now for the first time. So the book does this at several points, that it always repeats definitions in different settings. So this is now properties for this type of vectors.